The scalar product, I love highlighting definitions. Yes! You can also call it the dot product, so you can highlight that too, or the inner product. And I like calling it the dot product because you draw a dot between the two vectors, and then you invent a new kind of multiplication. Now that new kind of multiplication is kind of like matrix multiplication, except if you originally have one vector u, so let's call, let us call, try green. If this is vector u, and it has written as a column vector two elements u1 and u2, and this is vector v, v1 and v2, well, the dot product, all you're going to do is multiply the corresponding elements. So u1 gets multiplied with v1, u2 gets multiplied with v2, and you add them together. What does that kind of remind you of? Matrices multiplication. But in matrices multiplication, this first one was rotated at first, right? And then we rotated it and went to multiply it and add it, just like that. But now with vectors, they're already column vectors, and you just multiply the corresponding ones and add them. So it is very similar to matrix multiplication. And in 3 dimensions, you would have a u3 in here and a v3 in here, and same thing. They would all get, corresponding ones would all get multiplied together and then added up. So it's a relatively simple operation, and yet we're going to find out that the applications of this can figure out some really complicated math. So first of all, here are two vectors. Sometimes it might be easier to think of them as column vectors. So we have v is 2, -3, and w is equal to 1 and 2. If we wanted to find the dot product of these, well, we would multiply 2 times 1 and -3 times -2. And we would get the scalar product, or the dot product, of these two is -4. So if we had these vectors, 2, -5, 3, dot product with 4, 1, -7, you're going to get 8 plus a -5 plus a -21, putting these together, and you will get -18. Kind of like a matrices, but not at all. Perfect. I like that. So if you have vectors either in 2-dimensional space or 3-dimensional space, the dot product has some very common properties that act very much like numbers. Unlike matrices, the dot product one way is the same as the dot product the other way, because you're not having to rotate and crash boom into them, so the dimensions don't matter. They'll always match up as long. You can only do a dot product from 2-dimensional to 2-dimensional, or 3-dimensional to 3-dimensional. If you have a constant or a scalar in front, you can multiply that by 1 or by the other one. And if you're adding two vectors and you're doing the dot product in front, you could distribute and do the dot product, would do the same thing. And finally, if the dot product with 0, so if you have a vector that's all zeros, well, if you multiply all those things by zeros and then decide to add up all those zeros, you're going to get 0. So these properties are very much the same like real numbers, unlike matrices, which had a little bit of things that the order had to matter and stuff like that. Now, we also have some weird things that happen with the scalar product. Now, the first one, if you do the dot product of the same vector, so if I had 2, 3, and I did the dot product with that again, you get 2 squared plus 3 squared, which looks, well, that is a bad 2. 2 squared plus 3 squared, which looks a lot like a squared plus b squared. And we find a squared plus b squared equals c squared is our formula for finding the magnitude of any vector. So if you just do the dot product of the vectors, you get the magnitude of that vector squared, because you haven't square rooted it. Which is kind of interesting, but the craziest, most important, interesting result that we get from the dot product is this. Oh. So if I do the dot product between two vectors, it happens to equal the length of one times the length of the other times cos of the angle in between. Now, if we wanted to, we could set this up geometrically and we could prove this. We're not going to do that right now, but what this is going to allow us to do is this is going to allow us to figure out the angle between two vectors in a much easier way than it would be if we tried to figure it out geometrically. And this idea will also work in 3 dimensions. So you can just imagine how tough it would be to visualize. You have one vector in 3 dimensions, and then another one that intersects it, and then you're trying to imagine what's the angle between those two in 3 dimensions. And then how would I figure that out? And the dot product allows us to do that quite simply. So if you have 2 vectors and they're perpendicular, and here is your fun new word for the day. This is another word for perpendicular, orthogonal. So I don't know who made up the word perpendicular, but when you first heard it, you probably thought it was one of the weirdest words in the English language. And so they've introduced another one, orthogonal, which also is very well used in the English language.
Does the word have any relation to ornithology?
No.
Does it have anything to do with birds?
Ooh, but that's good, because look at this. We could just ornithogonology. Orthogonology. There we go. That's our new, happens to fit with what we're doing today. Now, if the dot product between 2 vectors, or the scalar product in between 2 vectors, is equal to 0, that can only happen if cos is 90 degrees. Because if we look at our formula, the dot product of 2 vectors is the length of the vectors, which won't be equal to 0, times by cos of theta. So if the left-hand side is equal to 0, then the only way the right-hand side can equal 0 is if cos is 90 degrees. And so now you can quickly find out if 2 vectors are at 90 degrees just by looking at their dot product. And if the angle is acute, or less than 90, then the dot product will be positive. And any time, because cos in quadrant 1 is positive. But cos in quadrant 2, so if theta is any angle between 90 and 180 degrees, cos in quadrant 2 is negative, so then your dot product will be less than 0. And then you'll know the angle between those 2 vectors is obtuse. And when 2 vectors are parallel, then the angle between will be 0 degrees. And since cos of 0 is equal to 1, 2 parallel vectors, the dot product is just equal to the lengths of those 2 vectors. rearranging that formula, we can now find the angle between any two vectors by just finding the dot product and divide by the length. And what makes vectors so powerful is that figuring out both of those things is really easy. So for example, in the past, if you knew this length and this length and this length, how would you find this angle? There's a formula. Is it an easy formula? Do you remember what it's called? Yes, has to do with my story. It's the coastlaw. Oh, wait for it. Wait for it. Okay. All right. So here we have three-dimensional vectors, and we want to find the angle between them. So we have our new formula. How hard is it to calculate the dot product? That's not hard. It's going to be 3 times 4, which is 12, plus 2 times a negative 1, which is negative 2, plus 1 times 2, all over. The length of v will be the square root of 3 squared plus 2 squared plus 1 squared. And the length of w will be the square root of 4 squared plus negative 1 squared plus 2 squared. And simplifying this, we get cos of theta is equal to 12 over the square root of 14 times the square root of 21. You can give your answer in radians or degrees. So if I now go to my calculator and go cos inverse of 12 divided by the square root of 14 times the square root of 21, I get 45.6 degrees. I already knew, since this was positive in the line above, that that angle should be something between 0 and 90 degrees. Had it been negative at this point, I would have found out that that angle would have been obtuse. So geometrically, if we think about what have we just figured out, okay, we're going to try and draw this This is going to be my x-axis, this is my y-axis. There's my z-axis. So I have the vector 3, 2, 1. So that would go 3 in the x direction, 2 in the y direction, and 1 unit up. I'll draw that one in green. And then I have the vector w, which is 4 in the x direction, negative 1 in the y direction, and then 2 units up. I'll draw that one in red. And I now somehow was able to figure out this angle there in between those two in that plane where both of those angles are. Now, if we had fancy rotational software, I could rotate this for you, and you would see that, oh, yeah, definitely looks like 45.4 degrees. Z goes up. No, because first you take your xy, and you imagine putting that on a piece of, on a table. And there's your table in 3 dimensions. Well, your table's bad. See? Oh, this is a pretty table. Look at the finishing work on it. It's like,
What is that?
yeah, students' tables suck. And then your Z is your vertical.
But what if you're doing it there? It'd still be coming out of the wall.
Well, then you would stand on the wall so it would look that way.
Oh, okay.
Yeah, it'd be fine.
It's like you draw something and then you bring it to life.
Yep.
Why? But you're only working two.
No, we have 3 dimensions here. So that's, so if I, like that with a nice looking table.
But does it go, it goes, like, is Z, does it only go up?
Z goes up and down. I could have drawn, but then you're going below the table.
So is Z, like, towards the sky, positive Z?
Yes.
Or
Yeah, towards like, okay, yeah. In this example, we've got 2 vectors. I'm going to write them as column vectors, but both of these vectors, there's vector 1, here is vector 2, and there is an unknown value m in here, but we're told that these 2 vectors, well, we're told we want to find all the values of m so that these 2 vectors are perpendicular. So if they're perpendicular or orthogonal, that means that the dot product or the scalar product, when you multiply these together, so when we do that scalar product, it's going to equal 0.
When you say perpendicular, you mean like according to which axis?
In 3 dimensions, so if I just use 2 of these smartboard pens as my vectors, right? It doesn't matter where I rotate those, as long as this angle between right here, which is looks like 90, right? Huh? Is it still 90? Well, it doesn't look like 90 from your angle anymore, but it's still 90. No matter how I move that around, right? It's still 90 degrees, okay? It's just hard to visualize that in 3 dimensions because it could be anywhere. But we're still considering these tails of these vectors put together, and we're finding this angle between them, okay? So there's 90. This would be less than 90. Any time that they point out like that, it'd be larger than 90. If it goes further, well, then you're now considering this angle on this side. Right? You never have an angle bigger than 90 between 2 vectors because they're always looking at the smaller of the 2 angles. They're not looking at this side's reflex angle. Then it would be a straight line and it would be 180. So if this is the case, then the dot product would be 2m plus 3m squared minus 8 equals 0. How do we solve an equation like this? We factor it, if it's factorizable. I'll rewrite it with the m squared first. Well, if you could factor this, the only possibility for the first one would have to be 3m and m. A little bit of guessing and checking will tell you this should be 4 and 2. The outside is 6, the inside is 4. If I make the inside negative and the outside positive, I'll get positive 2. Excellent. So m could have been negative 2, or m could have been 4/3. This is just a 0. Yeah, this is not a vector on this side. It's just a happy 0. Because the dot product is always a number. So we have the vector 4, negative 3, and we want to find a vector that's parallel to 4, negative 3. One that's not parallel to 4, negative 3, and one which is orthogonal to 4, negative 3. Now, I know that in your notes about the dot product, we happened across that if you do the dot product and they're parallel, that the dot product is equal to the length of both of those multiplied by each other. We're not actually going to use that. We're going to go back and use, because that would make this question harder than it needs to be. Okay? If you want to have any vector parallel to another vector, it just needs to be a multiple of that vector, a scalar multiple. So you could pick any value of k that you would like and multiply it by 4, negative 3, and you will get a vector that's parallel to it. So pick a value for k. 81? Negative 1. Okay, good. Whew. Negative 1, then negative 4, positive 3 would be an example of something that is parallel to you, but not the same as you. So you could have picked 2 for k. Another example would have been 8, negative 6. That's also parallel to that vector. One of the things in 2 dimensions you can do is, you know that slope, and you've dealt with parallel and perpendicular, you know that if 2 lines are parallel, they have the same slope. And when we think about a vector, when we think about something like 4, negative 3, the slope of this line is going to be negative 3 over 4. Why? Because slope is rise over run, which is your y values over your x values in a sense, but your x values are here and your y values are there. So that's why this sort of gets flipped as far as a fraction goes. So if you wanted something that's not parallel to that, you just have to make sure that whatever vector you choose here doesn't have that same slope. Notice that when we wrote 8, negative 6, if you did that slope, you get negative 6 over 8. And that reduces to negative 3 over 4. That's why they're the same, and that's why they're parallel. So you could choose any numbers here. If I pick 4, which is the exact same number here, what must I choose here? Not negative 3. Oh, the choices. Oh, 7. Okay, good. You could have chosen anything down there. That would work, other than negative 3. Now, for orthogonal to u, here we could say to ourselves, well, we could use the dot product here and say we need something so that when we do the dot product, it's equal to 0. And we have to pick something other than 0, 0, because 0, 0 is just a nothing vector. It actually, technically, you would have no angle between a vector and nothing. And that's why the answer would still be 0, because there's no angle. But if we actually want it to be a 90-degree angle, we need to have 2 values here so that the multiplication across the top and the multiplication across the bottom are the same, but one is positive and one is negative. 3 would make 12 here, and positive 4 would make negative 12 there. And if you added those up, you would get 0. So can you see the negative reciprocal thing that you learned back in grade 10 with perpendicular lines show up here? That all we've done is flipped it, and one of these had a negative, so that means if you think of it as a fraction, this one would have to be positive. Two vectors, find x if they're parallel. Find x if they're perpendicular. Okay, I'm going to let you try this one first. So we have two vectors. One of them is 2 and x. The other one is 1 and negative 3. If they're parallel, that means that these would be equal if there's some value of k multiplied by the other one. Can you see what k has to be if I put the k on that side? K would have to be 2. And if k is 2, then you'll also see that x would have to be negative 6. If they're perpendicular, that means that the dot product of these two vectors would have to equal 0. And that's not, oh, there's everybody who hasn't returned their textbooks. Perfect. Let's try that again. So the dot product would say 2 plus a negative 3x would have to equal 0. So 2 is equal to 3x. Divide by 3. And you get x would have to be 2/3.
In the first one, do you have to say what k is?
No, you wouldn't have to say what k is here. I'm just showing a method that would work to figure it out. It's easy enough to see that, oh, it has to be negative 6. But if the numbers weren't as nice, right? If I made this 7, then you're like, ooh, what would have to happen here? Well, maybe I would even have to say 2 would have to equal 7 times k. So k is going to be 2/7, and then x is going to be negative 6/7 as a result. But it wouldn't be as easy to figure out. All right, so there are some questions for practice. I'll hand those out to you.